Hello, everyone. This is section 9.2. We're now going to take the idea of that confidence interval for the mean and roll it right into hypothesis test for mean. Because we have already reviewed hypothesis tests from chapter 8, I'm going to move through this pretty quickly. The idea is almost exactly the same as the hypothesis test for proportion, except for the way the conditions will be a little different, and then the way you find your test statistic, of course, is different because we have different p-hats, no p-hats, q-hats, we have x-bars and that sort of thing. So here we go. I'm going to generalize first, and then I'll do two examples, and then a third little example too. That's a little different. So conditions, just the same as they are for the confidence interval, so it must be a simple random sample. Oops, you must have a normal population or a large enough sample size, and remember for us, a large enough sample size is greater than or equal to 30 for this. So there's one more condition that's a little bit weird that they ask us to write, is that the standard deviation of the population, we must know that. Typically we won't know that, which is section 9.3, so we'll learn how to deal with that. But if we do know it, that's one of the conditions for this test, okay? And then the last one, sorry that I didn't write on here, is population at least 10 times the sample. Kind of a weird condition that the standard deviation has to be known, but there is a different test if we don't know it, so that's why we need to write it in there. Number 2, our null hypothesis is going to be just like it is for the proportions. Remember, in the proportions we were saying that the proportion is equal to something. Now we're just going to say the mean is equal to something. So we're just going to guess the mean, and that's going to be our null hypothesis, just exactly like it was for proportion, but now we're guessing a mean instead of a proportion. The alternate, just like it was for proportions, can be one of 3. It might be not equal to what we think it is, or less than or greater than, depending on the context of the problem, and they will always tell us. Okay. The third thing you're going to do is compute the test statistic. The test statistic is going to be found the same way we found the other one. It's what we got, which is x bar. Okay. I'm going to write down, just so you see it, I'm going to write down the proportion one, p hat minus p naught over the square root of p q naught over n, right? So what we got here is x bar. What we expected to get in this one was a hypothesized proportion. Now it's a hypothesized mean divided by the standard error. The standard error for the proportion is pq over n. The standard error for the mean is standard deviation of the population divided by the square root of n. So it's a different formula, but it's formed exactly the same way. So you might say, no, that's not the same formula, but it really is. It's formed exactly the same way. Once you find that test statistic, got to find a p-value, just like we always have, same way. That doesn't change how we do it. And then you compare your p-value to your alpha, or you can compare your z to your z star just to figure out, but you got to have both on there. Then you decide if you're going to reject or not, and then you write the conclusion, same way we've done it before. So I'm going to walk you through a two-tailed test and a one-tailed test, and then another type of question they could possibly ask for. So I'm going to start with a two-tailed test. I'm going to be a little quick because I know you don't want to watch these videos forever. And if you are comfortable with this, you could probably just roll right into the homework right now, except for the third part. So you might have to kind of flip-flop or fast forward through until you see me erase the third line here. So the first one is, we have a population standard. I just shortcutted this to write it down. Standard deviation 150 in a simple random sample of 4 students. The mean SAT score is 1173. Test the claim that these students come from school X, which has a mean of 1345. So I'm going to skip the conditions. I'll do that more in class just to save the time right here. And I'm going to write these things in symbols instead of words, all to save time. And you can do that in your homework for sure. But remember, on this next big test that we have coming up at some point here, got to write it all out. So we think that the mean is 1345. That's my hypothesis, because we think they come from school X. The alternate is just not equal to. We're going to decide whether we think they come from this school or not. Okay. I will tell you that the SAT scores are normally distributed because that is an important condition. So now we're going to find a test statistic. So it's what we got, What we got was 1173. Sorry about that. 1173 minus what we expected to get, which is the 1345, all over the standard deviation of the population divided by the square root of the sample size. I'm going to do this math really quickly here. Minus 1345 divided by 150 divided by 2, yeah. I got a test statistic of negative 2.29. Just like any other problem, we need our critical values on here, which for this one are negative 1.96 and 1.96 because no one told us otherwise, right? 5% alpha. Looks like we're in the rejection region. We're going to find a p-value. P-value is normal CDF. Remember the p-value. Here's my negative 2.9. It's out here and it's out here. Sorry for that bad normal curve there. So let me erase that. So it's normal CDF from negative infinity to negative 2.29. And we're going to multiply that by 2. If it was a one-tailed test, we would not multiply that by 2. So negative infinity to negative 2.29 times 2, 2.2%. In any case, we're in the rejection region. This is less than the 5%, right? So we reject the null. So we say there is evidence that the mean is not 1345. And more specific to the context of this problem, there is evidence that they did not come from school X. All right. Next example is a one-tailed test. So this time the claim is the mean study time per week is greater than 1,015 minutes. In a simple random sample of 64 students, the sample mean is 1,050. Test the claim. And they tell us the standard deviation is 150. Again, we'll assume normal distribution. My null hypothesis would be the mean is 1015. The alternate is what we're trying to show, right? That the mean is greater than 1,015. Is there a claim is a study is more than 1,015? So that becomes my right-tailed test. So only one critical value this time. So all 5% goes on that side. So I could do an inverse norm of 0.95, which is going to give me a 1.645 for my critical value. Make sure the critical value is always there, yeah. Now here we go. My test statistic is what we got, which was 1,050 minus what we expected to get, divided by standard deviation population is 150, divided by the square root of the sample size, which was 64. 150 minus 1015 divided by 150 divided by 8. 1.86. P-value, normal CDF from 1.86 to infinity. No double this time because there's only one tail. So we go normal CDF 1.86 to infinity. We get a p-value of 3.1%. No. Oh my gosh, yeah, that's right. Sorry. 3.16%. In the rejection region, 3.16 less than 5%. In the rejection region. I'm going to stop writing right now and go to the next example. We're going to reject the null hypothesis. We're going to say there is evidence that the mean is greater than 1,015. All right. The third one is just a little other things that they can ask. Ultimately, in class on next week, I'm going to show you how to do these on your calculator so you're not finding the test statistic by hand and you're not finding the p-value by hand. You're going to like that little trick. However, there are still types of questions I can ask and the AP test can ask that you know how to use the formula. What's going to happen is you're going to forget about the formula ultimately. So here's the next question. It says, a simple random sample of 100 SAT scores is to be taken from a university with a standard deviation of 150. The null hypothesis is the university has a mean of 1175. Find the values of the sample mean that would give you a p-value of 5%. So now we're going to kind of work backwards. I'm going to erase this if that's okay here so we can see a little space better. All right, so a couple of things. So remember, if we're going to have a p-value of 5%, I should say, sorry, two-tailed test. This is important on this one, how that came from, right? So remember, if we have a p-value of 5%, that came from a test statistic that gave us some test statistic that came from, right? So clearly we know that test statistic, right? Because if it's when we just do an inverse norm of 0.025, but I can do it anyway, we get a 1.96. So that means my test statistic, to give me a p-value of 5% on a two-tailed test, my test statistic had to have been 1.96. So I'm going to take that test statistic then. And shove it into my formula, because the question was find the values of the sample mean, right? Here we go. 1.96 equals x, really that alone, minus what we expected to get. So the null hypothesis was 1175. The standard deviation of the population was 150, and my sample size was 100. And now we just solve this equation. So this is a really good example of having to use the formula, because again, I'm going to show you how to do these problems without a formula, or how to do the test without a formula. And you're going to, oh, this is great, but then you're going to forget the formula. So these are the types of questions you can get. I'm going to finish this problem. So I guess 1.96 equals x minus 1175. 150 divided by, whoops, that should have been square root of 100, yeah. So 150 divided by 10, which is 15. So we're going to 1.96 times 15 plus 1175. So that's 1204.4 roughly. So that's one value of the sample mean. Remember, there's another one on the other side there. Remember, so that this was my, sorry, this should have been a negative 1.96 there, right? That one was this one. So now I just have to go back and do the other one. And I'll stop right now with the example. But you go back and do a negative 1.96. Actually, I can do it. It's so easy. And I'll be done. Negative 1.96. So negative 1.96 times 15 plus 1175 gives me the other answer of 1145.6. So these are the two values that would have given me a p-value of 5%. So check out that homework. We'll go over it on Tuesday and then add on. Have a good weekend.